So we have quite a few people online now, and I was just going to give a little bit of background about CMC, just for those of you who haven't heard of us. We're a not-for-profit. We were formed 43 years ago when Pierre Trudeau gave $1 million to a professor at the Queen's University to actually help students to access fabrication facilities at the Nortel. And Nortel really wanted someone to be there to clean up the designs and to make sure that they were fabricatable and to handle all of the support questions. And so that was how CMC, the Canadian Microelectronics Corporation, was born. And since that time, we've added a lot of new services. So now we provide CAD tools in the cloud from a variety of different commercial vendors. We aggregate designs together. We use over a dozen foundries worldwide to provide people with samples of microelectronics, photonics, microelectromechanical sensors or MEMS, and even superconductors. And recently we added on a quantum group. So we provide training and fabrication of quantum devices as well as quantum coding onto a variety of machines. So we're actually global. We have customers in over 22 countries, and only the Canadians, of course, are subsidized by the Canadian government. So our most recent funding program is called Fabric. I hope you've all heard of it. And the webpage is fabricinnovation.ca. And under that, we were given $120 million over 5 years, both to support academic usage of all of these tools and technologies, but also to support startups. And so we have been rolling out cash to startups, subsidizing them to develop their next-gen IoT device or to develop process technology, which is where the CPFC comes in, of course. We want the CPFC to be able to create new process technology, which we will then market and make available not only to Canadians, but to our customers worldwide. So it's a very, and we sort of chose a few pillars: compound semiconductors, photonics, MEMS, and superconductors as being areas where Canada can punch above its weight. It doesn't require the same sort of capital commitment that you do for a state-of-the-art CMOS fab, and we can use our smarts and the existing facilities in Canada to expand on all of this. So that's the whole Fabric story, and very soon we'll be doing a defense call for Fabric, where we're looking for dual-use technologies, and we'll amass a number of projects. To date, we've been running Fabric for about 2 years, and we've committed $25 million worth of the government's money for $68 million worth of projects. So to me, that's a big win. And there's also been an awful lot of training that's been funded through the Fabric program. So Velco has some exciting news, which was just announced this week. Would you like to talk about the CPFC a bit?
Thank you. Thank you, Gord. Great introduction. I would like to share some great news. We receive marching orders from our government to start the process of scaling up CPFC capacity and capabilities over the course of the next years, while changing the business model to a commercial business model, which will allow us to attract private investment and properly fund the journey going forward. Perhaps just to give you a little bit of background of CPFC, and in a similar way, Gord described CMC journey 20 few years ago in the process of divesting some of the Nortel asset. The Research Council actually acquired expertise, intellectual property, people, and equipment, and raise funds from provincial and actually federal and provincial sources, from province of Ontario and the federal government, to build the regional facility. And the facility was actually originally designed to be more of a prototyping facility. Fast forward, we move from prototyping to supporting clients to move from development to new product introduction and to manufacturing volumes, which actually significantly increased the demand. Was due to the increased demand to offer manufacturing capabilities. So today, if you look at the Canadian supply chain, we usually intercept the marketplace supporting clients from development to full-scale manufacturing. And when they scale up in volumes, that puts a lot of pressure on us to scale up our capabilities and our capacity. Perhaps a couple of comments on the modern world, because in the original type of framework, we have been focused on more telecom, the lasers that drive the traffic anywhere from the backbone to the metro access and fiber to the home. Today's world is mostly driven by AI and quantum innovation, and that actually changes not only the type of clients we work with, but also puts additional challenges to develop the processing technology that we can support our clients. The business model is pure play, which basically means clients come with their own IP on the design of the devices. Protecting their IP and not contaminating their IP is very important for us. But when it comes to process IP, we develop it internally, and that's how we built our intellectual property, which actually defines one of the biggest assets of the fab. Now, what is happening in the current world is large volumes are being driven by the datacom and high performance computing market, but we have been always having and nurturing a very healthy number of companies related to defense, aerospace, security, and that's very important for us because that provides significant Canadian content in their supply chain. It also certain level of related to national security and sovereign type of supply chain. And it's very hard to describe all the applications, but just to give you a few ideas, a lot of the sensors, fiber optic sensors, for example, that go to planes and aircrafts and drones and all that require sensors that need 3.5 devices, lasers, for example, or gain chips or detectors and all that. We have applications also in rangefinders and lidars and all scope of other applications that people consider to be dual use, but they have a significant footprint into the military interface supply chain. And I probably will stop here because I'm pretty sure there are other questions and other comments that the audience may want me to comment on. Thank you.
Well, maybe we can have Gord weigh in to frame, maybe define what dual use is, because I think for some people, dual use. I know my experience is the dual use concept's been around in semiconductors for a while. I've written about rad-hard systems and how really reliable systems built for aerospace or even outer space, they eventually trickle down into automotive, for example, because reliability is so important. But maybe we can start with you, Gord, and to what is, what would an explicit focus on dual use to deliver? Because I know Fabric is already pivoting a little to kind of focus on more of a dual use technologies, opening projects with applications across different industries, and certainly we see the government very much being very vocal and explicit about their intent to bolster defense capabilities, and certainly it seems there's a recognition that semiconductors are part of that.
Yeah, so I take a very broad brush to dual use, and there's some things that I think are wrong in the system that funds defense research and so on. So one is that I really do think that we need to address civilian emergencies first. And so we need to provide technology that's useful for search and rescue, for first responders, for police, firefighters, all that sort of stuff. And those technologies have lower barriers to adoption. You can build a product and you can start selling it to civilian emergency agencies all over the world and NATO nations and all of our partners in the middle powers, shall we say. So I think that is very important. In order to get revenue into the company early on, defense has very, very high hurdles for purchasing, and they don't pay for R&D typically. They don't pay for testing and field trials and all those things. They will offer you the use of one of their areas for testing a product, but you have to bring the product fully baked to go there. And some of these programs that they offer now only go to prototype and then stop there. So there's not a defensible product by the time finished. So what we want to do is fund and government being government, it's very difficult to fund one person in their basement. So what we really want to do is find a company that has some resource and has maybe a product already going, and they want to get to Gen 2, where they want to get to a viable product. So they have to be able to pay for the development for at least a quarter, and then we can give them back their subsidy, so on. So right now, the way the fabric works is you define a project which is maybe 1 to 2 years long, and you get 37 to 40% of your expenses back quarterly as you file reports. So I envision that Duet would be about the same thing. So you have to have some resource, and it's I think doing a next gen product is going to be a sweet spot for us. And these projects will be anywhere from $500,000 to $10 million. We want to put quite a lot of money out and get the things rolling. Right now, we're kind of running in the $200K to $2 million range. But the other end of the problem is when you get to the end, you've got a prototype. Well, defense doesn't pay for all the testing and modifications and things that they want. So we want you to do field testing and hundreds or thousands of units and support you fabricating those with subsidy so that you can actually get to a sort of TRL-7 product by the end that you can actually sell. So I think those are the important elements of Duet that are different from other programs. And of course, we at CMC have a network in Canada of 69 universities, but we have several hundred outside of Canada that we regularly deal with. And so we have access to lots of different technologies. If there's a piece missing to your project and you need some help, either these institutions around the world or the CMC employees, we also have a heavy technical staff internally who typically do support, but could also do development work for folks. And so those are the kinds of things that we want to look at. So if I pick a few examples, there's a company in Ottawa that makes censored insoles for shoes. And these insoles gather data about your gait, and they're using it to monitor Parkinson's and multiple sclerosis and determine how well people are doing with the disease. But that could just as easily be used for first responders or for military folks to see are they on their feet? Are they limping? Are they dragging? Whatever. Some other folks in Quebec are doing flexible electronic patches that can monitor, just like these rings and watches do, but they can monitor dehydration and blood oxygen levels and all those things. All useful stuff for first responders. And obviously they'll have defense applications. When it comes to lasers, there's a company in Quebec that does accelerometers and gyroscopes that are entirely optical, and so they need lasers to stimulate those. And because there are no moving parts and they're very low power, those are great for aerospace applications. Out in Saskatchewan, there's a professor who has created a company that is providing rad-hard microprocessors. So again, they're immune to single event upsets up in space. And so there are so many technologies flopping around Canada that could use a boost and could use some help and some visibility, and maybe applying AI to them, as an extra step, or maybe creating a better sensor, a quantum sensor perhaps, is just going to put them over the lip to a really saleable product worldwide. Another company we're talking to makes a very small radar system that can detect other drones, and it's small enough to be mounted on a drone. So all of these things have great applications, human applications, civilian applications, but obviously there are parallels. And by the time the military, has got around to looking at the product, it'll be for sale. There'll be thousands of units out there, and they'll be able to really see its reliability and functionality and have a really good flavor for it. So I think that will grease the wheels for military procurement eventually. But in the short term, we need to build things that we can sell.
In the same sensors that can detect a drone, they can also find people during a disaster or a lost puppy. So that epitomizes the dual use concept. I know that I see quantum AI getting a lot of attention from the government, and it's really highlighted in the defense industrial strategy. But something I know, and I think we, three of us all know, is how important photonics is to AI, and partly the reason because photonics is not new, but I feel like it's becoming really cool. And I view it as someone who writes about the technologies as kind of a really important workhorse to enable quantum, to enable AI, and of course now we're moving, what they call co-packaged optics, or CPO. That is getting a lot of attention and a lot of growth, and it's just because to do AI, you got to move a lot of data around. And we need to do that efficiently. We need to do it with regard to power consumption, which is a whole other rabbit hole we won't go in. But all this does take power. So maybe Valco, you could speak to because maybe not everyone on our webinar understand exactly what photonics are, and what do photonics make possible, especially in our real world that maybe people don't realize.
Well, it's obviously a topic that I can talk for hours, but I'll look through the lens of what drives AI and high-performance computing nowadays, and I'll start with the problem statement. So if you look at the Moore's law, and you're trying to squeeze as many transistors in a small footprint, you actually reduce the size, you increase the density, and you go to the next generation node and the next node and all that, and you go to a physical size that you pack so many of those devices that if you keep packing, the whole chip is going to explode, and you don't have the Moore's law scalability going forward. So what people realize at a certain point is I actually have to connect multiple GPUs and CPUs and memory chips so I get the functionality I want to get. The question is, when you actually start connecting them, you need the highways to connect them. And if the highways are driven by electrons, you actually have a limitation of, first of all, the capacity of the links, which is basically the capacity of your highways, and then generate way too much power that you need to dissipate, which actually converts your design and in your data center and all that in one big heating machine that you can, and you have to cool off. And if you have to cool it off, all the people with engineering and physics background know that it takes more energy to cool off rather than to heat up. So you don't want to do that. So this is where the photonics comes, because the photon actually can travel faster than electrons, and they can actually generate much less power that you need to dissipate. So you're actually solving two problems. You have the fast speed, and then you do not dissipate as much power, which drives down your power consumption. So so-called optical interconnects become a big item now, because they actually connect all these. These are the highways that actually connect GPUs and memory chips and all that. And now, if you look at the space, how you solve these connectivity problems, one of the existing status quo type of solution, which also evolves in terms of speed and feature size and all that, is to use optical interconnects. which are pluggable devices. So in some of the cases, like transceivers, for example. So you have standard devices, you plug them in, you actually have emitter and detector, and this is how you communicate. Now, if you want to package even further, use less energy, have higher density, have higher speed, and smaller footprint, you need to use near package or co-package optics, which basically means you have to co-package your sources, your silicon photonic circuits, and your electronics in a very compact package, which results in very high speed and very low power consumption in a data center. So that's kind of the essence of the photonics penetration into the space. And in a way, this is just the first wave, because there are other things that are going to happen. Moving from point A to point B and back, building highways in terms of optical interconnectivity is one thing, but then manipulating the photons in terms of routing and switching and all that would require further photonic penetration into the core of the data centers and in the core of all the switching and routing logic that happens in the data centers. So it's just the beginning of that huge wave. Now, how quantum mixes into the space? When people talk about quantum technology, they typically understand that there are three fields. One of them is quantum sensing, quantum computing, and quantum communications. And they have different level of maturity, and they have different level of penetration of photonics into that. Because if you look at the quantum computing, and I'm not trying to oversimplify the world, but if you look at your qubits that are the heart in the quantum computing, they're either electronics or photonics, and both of them have certain advantages. So if you look at a company like Xanadu, it's a photonics core. So the photonics is the technology behind that. So if you look at optical connectivity, probably 100% of this will be based on photonics. And everything.
We actually have a question in the chat. Is optical also used for inter-IC communication for AI compute? And I think it's plane-to-plane and rack-to-rack today, but there may well be optical transmission on board.
It's a great question, because that's how the world, in my humble opinion, is going to evolve. Because right now you get, the first penetration was actually data center to data center, and it was rack to rack, and there's going to be inter-rack as well. So it's just the same way fiber optics penetrated into the communication is going to happen in the same way. So you start from the longer links and you go to the shorter links in a way. So that's a great question. That's how exactly things are going to evolve, in my opinion.
A story I like to tell is in a typical data center, if it's serving Netflix to you, about 10% of the energy they require is sending data between computers within the same data center, not outside but inside. But if it's AI, about 50% of the energy is used just transferring data back and forth between racks, between planes. So there's an enormous power savings that you can make by changing that to optical networks.
That's correct. Now, the implications on the technology roadmaps of the companies and the ecosystem in the space is that the photonic devices that are going to drive the traffic over 3 feet versus the one that are going to drive it over 2 kilometers and a few hundred meters, there'll be different technologies and there'll be different devices. It's I don't want to have a kind of very in-depth technical discussion, but I mean, the shorter the reach, you can count on pixels and micro LEDs. The longer the reach, more expensive lasers you need to use into the mix. So that's how this is how the market is going to be segmented in terms of application areas and the technologies and devices. So if you look at the portfolio that CPFC has today in terms of clients, we pretty much serve all of the above in a way.
And so you hear a lot about drones being tethered and having a fiber optic that rolls out behind them. They all need lasers and they need photonic ICs to do all of that encoding of data from the camera down to the down to the person who's got a headset on.
Well, also some of the guided systems actually use infrared optics, and the source is actually one of the multiple mechanisms to guide a drone or a warhead or whatever it is.
Yeah, another thing in Canada, the INO developed infrared, uncooled infrared that works at room temperature using vanadium oxide bolometers, and they transferred that technology to Teledyne. So we have a capability of doing infrared cameras, but then Teledyne also does CCD imagers, so you can do visible imaging and infrared and on the same chip. And so that's a really intriguing multispectral sort of application for either finding people in forest fires or underwater, or but also obviously military purposes.
Before we launch into the future and everything that's possible, I wanted to take a step back a little bit, because we wouldn't, how did we gain all these capabilities? Because there's some heritage here that's important as well, that led to the creation of the CPFC. And I speak as someone who started my career in Ottawa when Nortel was very much spread across western Ottawa and Canada, and we had photonics companies. I recall JDS Uniphase as being a company I wrote about regularly. So how is that heritage and the history? How is that guided the evolution of the CPFC to where it's got today?
Well, that's a great question, and I will try to. Yes. I will probably try to answer from just trying to look through the lens of a business model in a way. So if you start business today, people use different framework. They use SWOT analysis, and they use the Porter models of positioning yourself in the ecosystem. But it doesn't matter which model you're going to use. You actually have to build on some existing strengths and assets that you have in this particular case in the community. You have people who understand photonics, and a lot of them are in town or in the cross proximity. And photonics business is one of those that you have multiple clusters in that. So that's a significant type of asset. And then you have to look at the supply chain, because if you're a fab, typically you drive around you a pretty well whole ecosystem. Your companies that you work with, they want to have their design teams nearby. And the other way around, if you have a good design teams around, you can actually work with them, and then you can build further your capacity and capabilities. And then you actually need a full supply chain upstream and downstream, which actually is also very helpful, because you have past Nortel, all the heavyweights that drive a lot of innovation in Ottawa and the ecosystem, and they also create opportunities for spin-off to grow and scale up. So I think it's if you look at I can speak from the perspective of fabs. If you look at the history of the current fabs, in our space, in the 3.5 space, all of them actually have a legacy that goes back to assets that have been developed over the years based on certain core expertise that existed in a particular region of the world. I can give a lot of examples. There is a large cluster in Eindhoven. Why? Because this is an old Siemens facility, and Siemens is out of this business, but it actually created the ecosystem, so a lot of companies flourish there. If you look at other places in the world, like Singapore, AMF that was recently acquired by Global Foundries. Why they're there? Because there was a very heavy investment over the years in an organization called A-Star, which is the equivalent of NRC in Singapore, and it can go on. Actually, TNC was created because of ITRI, which was modeled after NRC as a global RTO, years ago.
Mhm. So the other technology that's related to photonics, and maybe we can speak briefly about that, is compound semiconductors. It's another technology, as I understand it, that's very, it's one of those capabilities Canada's strong, and that's how the Fabric program was architected, was to focus on these strengths that we have and just and build on those. So maybe we can talk a little bit about compound semiconductors as it relate, because they also fit into the dual use capabilities.
Yeah, so we talk about silicon. Love silicon. I've worked in there for 40 years, but it's a natural semiconductor. You can make it conduct or not conduct relatively easily by changing the temperature or putting what we call a dopant, but an impurity in it, phosphorus, arsenic, boron. So silicon's been the real workhorse, and it also makes a nice insulator if you just put oxygen on it. It grows an oxide, it's glass. So beautiful material. Compound semiconductors come from the two columns of the table of the elements to the left and right. That's why silicon's in column 4. So they call them 3 5s because they're in column 3 and column 5. And also there are some that come from columns 2 and 6. So you combine them together, and it is weird and wonderful. And then you have to do all sorts of specialty stuff with ultra thin layers to make them, which we say blend the behaviors of the two different materials so that you get an interesting result. So they do semiconduct, but the nice thing about them is that they can also interact with light better than silicon can. So they can absorb and emit light directly, and you can create lasers right on them. But also, they can be much higher speed. They have better electron mobilities than silicon. So you can make very fast transistors in the hundreds of gigs, and you can. And you also go to very high voltages with them. They can be engineered with a much higher band gap than silicon. So this is why we have GaN switches at 600 volts for automotive. And for data centers are doing level translation as well using these things. And then very high speed power amplifiers that are used in satellites and that sort of thing are all built in these. And another thing that's interesting about the compound semis is they are inherently rad hard. So the starting material is difficult to produce. They are difficult to process. It's a great opportunity for Canada because we have the smarts of Velco and his team to actually turn those devices into something really useful and high performance. So it's quite a unique capability. And most of Velco's quote-unquote competitors only do part of the process. They don't necessarily grow their own substrate, or grow their own layers. They don't necessarily pattern them. And so I think together with CMC's design team and the funding we have, we can create some new process technology that will be really world-beating. And obviously being rad hard, being high speed, all of the above, that can make a huge difference in military applications. And the switching efficiency is far better than silicon as well, so you can reduce the power losses. And that's why suddenly you're seeing, when you buy a computer, you get a tiny little adapter that goes in the wall. It's typically GaN devices that are in there doing all the switching. I noticed Mustafa Jaffer has said that we have world-class photonics research. Yes, we do. I grew up in the 80s and 90s when university labs could actually build transistors, but that's not the case anymore. They couldn't keep up with the transition, and so they switched to technologies that don't scale down as aggressively. And so MEMS, you can only make something beam so small before it breaks and isn't functional anymore. And photonics, you're limited by the wavelength of light, and so you don't go down to 1 nanometer in a photonics device. In fact, the performance gets much worse the smaller you make the waveguides and systems. So those are great places for Canada to be. We have all the smarts, we have all the equipment, and when you buy the equipment, it's good for a decade instead of a year or two. So that is a great place for us to operate, I think. We do have a lot of photonics research being done in universities, and we have a page. If you look at globalnanolab.org on the internet, you'll see an international collaboration between nanolabs. And if you click on the Canada or the CMC tab, you'll see that there are 47 some odd fabs across Canada. I've just asked the NRC if we can add their labs to that as well. And I think that'll give us something on the order of 80 labs that are all in very specialized kind of circumstances, but very strong on optics. And Lucia, what used to be INO, also have a lab and do some really amazing stuff. We've got a question here.
Well, perhaps
on IP. On IP.
Well, I mean, I can try to address probably the first part of the question from Mustafa. It's the way a fab looks through the lens of IP is, the IP that we develop doesn't get patented, it doesn't get publicized, it doesn't get fabs keep their IP as a trade secret or know-how, because the moment you publish a patent, then you tell to the world what is your secret sauce on processing. So when it comes to the IP that comes from academic institution, we have to figure it out. Is that a process IP, is this a material IP, or is this photonic functionality or device IP? So if it is for device, it's probably our clients who are the organizations that might be interested in that. And I'll entertain conversations with all the leading institutions in that field to guide them through the process of who will be appropriate parties to go and work with the IP. I mean, Canadian party, because we didn't want to have exposure of this IP on any risk. But if it is process development technology, that will be of direct interest from fab perspective as well.
And you can see some more comments from Lucia in the chat as well. So someone's asking about IP. It is true enough that if you go to the US, typically funding rounds are 3 times larger. They're much easier to get than going through due diligence in Canada. And valuations of companies when they're ready to sell are larger in the US and Europe. They really see value in Canadian firms and the IP. So that is a problem. One thing I really liked was, for years I've been promoting the idea that if the government put in $2 for every $1 that an angel or a VC put into a company, then they would get rounds as big as they could get elsewhere. And the due diligence would be done by the angels, it would be done by the VCs, and then they'd get a much larger round so the company could move faster and grow bigger. And NACO, the National Angel Capital Organization, they saw a $1.75 million, $175 million budget being approved for, was it? No, sorry, $1.75 billion. The Canadian government is approved for stimulating the whole venture network, and they suggested that $750 million of that should be what's called a sidecar fund, where venture capital goes in for $1, Canadian government goes in for $2, and if there is an exit, the Canadian government actually benefits from that exit, and they can use the money for new investments. And hopefully some of that money could be used for Canadian companies to buy smaller Canadian companies.
Yeah, that's a good point. But going back to the IP, because it comes from the academic community, I probably can share a few things that I found a little bit challenging. One of them is if you pick up randomly several universities in Canada, there is a total difference in the IP policy. Some of them IP belongs to the university 100%, some of them 100% to the inventor, and everything in between. This is very challenging for an organization that wants to license or commercially explore the IP. So I think there is some sort of a need to change that and make it more consistent. The other thing that I notice is universities actually have centralized units to manage IP licensing and commercialization. And a lot of them understand how to do it for life sciences. If you're in drug development, it's one thing. But if you go to photonics, electronics, areas that we understand, the model of licensing this is completely different. So developing this knowledge and expertise of putting the IP in different buckets for different purposes and for different verticals, it's extremely important to be able to maximize the value of IP and minimize the risk of losing it or yeah.
You've hit my hot button there. The technology transfer organizations often don't have great knowledge of everything they couldn't possibly. But also they seem to think that it's worth billions and everyone on the planet needs it. So it's really hard when you do a negotiation with them, and they want to get cash out of the company early on to help pay for the fees they've already paid for patenting and so on. And for a startup or a small company, cash is the worst thing you can take out of them. So there is an organization called SAIL. It's howtosail.org, and they proposed a simple agreement for intellectual property licensing, which is equally painful for everybody, but if there's a win, everyone wins. And this sort of mirrors the SAFE, the Simple Agreement for Future Equity, which is used for a lot of funding. So I would love the Canadian government to impose that. They fund the universities. They should just say, here's your IP policy. Off you go.
Well, keeping IP, I mean, that goes back to the heritage. We had this IP and the skills that we didn't officially. In some ways, we probably could have done more. Well, we know we could have done a more formal effort to maintain, the IP of a company like Nortel. But I'm just the other word we hear about a lot is sovereignty in relation to defense and dual use. And I'm wondering about how do you balance, scaling up, getting these technologies out there so people really benefit. The country can benefit from them, and the companies that come up with this stuff actually it's worth their time. They could build a company and it's not as painful. But we talk here a lot about sovereignty. So I don't know if that's something you either you want to weigh in on, because Minister Solomon, I've heard, talk about sovereignty is not isolationism either. It doesn't mean keeping everything in the country. And it's good that we have these capabilities in this IP, and I think the CPFC is just an excellent example of something that we have. We should maximize its capabilities and get the most of it. But how do we balance these concerns around sovereignty in the current climate?
Gord, this is a difficult question, so I'll let you go first.
Thanks. Yeah. Well, I think we really need to find places where we can compete on a global scale, and so places where we can demonstrate pure superiority, and we'll take in other people's. You were talking a bit about IP in the processing of Elco, but what we do is a process design kit that allows you to design devices, whether they're photonic or rad-hard or whatever, in a process, but it doesn't tell you anything about what machinery was used, what flow, what chemical, what temperature, what voltage. You know nothing about how the process is done. You just know that if you do this shape, you're going to get this result. And you can only put the lines so close together, and the lines have to be a certain width, or else they won't work, and so on. So those PDKs, I think you can put those out really freely everywhere, and they don't tell you exactly how the process works. I love that fact that we can develop process technology in Canada, and as I say, we pick these 4 pillars that we thought that we could really punch above our weight, and continue to advance on those. So I see there's a question about how do we avoid ecosystem fragmentation. Well, we really want to have an ecosystem of small university labs that can do really strange materials and really bleeding edge kind of research stuff and publish it. But then we want to have some mid-range fabs that will do smaller volumes, that will take people from the university environment through to hundreds, thousands, tens of thousands of devices. And then finally the big fabs like Teledyne Teledyne, world's largest open source foundry for NEMS, but they can also do photonics. And so they will only look at you when you got to a certain size. Obviously, just they don't have enough engineers to handle all the smaller guys. But we need to make that complete end-to-end integration economy so that we can do all of this. So Velco is going to make the world's largest compound semiconductor fab. That'll need to be some smaller fabs around that will feed him with new ideas, new customers, and new processes.
So, Gord, I think thinking in this line of thoughts. One of the challenges is, I'm speaking from the perspective of photonic photonic fab, which is 3.5 fab. There is still a lot of proprietary process development. And I can tell you one of the challenges that we experience is a startup, an SME who work with university facility, and they'll develop a process on a set of equipment, and then they'll hit the capacity, and they want to move from prototyping to NPI, and they'll go to CPFC. And very often we have to actually start from scratch. And the process is that there is no cross qualification of the equipment, so we can actually move a process from A to B to C. So I think the secret sauce of that is making sure that there is a certain level of cross qualification of the equipment, so we can actually move processes from R&D to development to large fab. PDK is the tool that can actually facilitate that. But there are other things into the mix. But I wanted to go to the original question Gary was asking about in the world of sovereign type of desire and how we framework that without kind of self-isolating ourselves and all that. I think one thing that I've seen in the semiconductor business being done by Japan, by the way, is they took the exercise to map all their existing assets from research and development to manufacturing, and they actually map it in a process of developing a semiconductor strategy. And they intentionally said we are not gonna do that. And this is the most difficult thing in the world. You say I'm not gonna do that because I'm behind. I have no chances to be competitive, and I'll go and partner with country A or B, and everything else that is considered to be strength, we're gonna invest in build. And I think what I wish Canada can do is to do that mapping and say we are not gonna do that, and go through that thought process and position ourselves on the global scale.
Mm-hmm. Yeah, sometimes what you decide to ignore is just as important as what you decide to focus your efforts on. And that goes back to focus of fabric on things that we're good at, scaling that up, and scaling up the CPFC, and there's a lot of discussion. I mean, I've noticed it over the last 6 months. This very big shift to how we're discussing about defense, explicitly talking about defense, and I started DIS. The DIS talked a lot about quantum AI, but now we're there's some awareness. You need semiconductors to do this, and photonics, and I think I suspect I don't know and maybe you can talk about it or not, but I feel like the timing of the CPFC and its next stage is very much in alignment with what's going on more broadly. And this is
there's a historical precedent for this because spoken on our last webinar we talked about how defense sometimes when they are the first customer they can spend a lot of money to get the technologies because sometimes they are willing to spend a whole bunch of money to make it feasible to do, and then we have technologies. Those technologies stay with us. So I think do we have any thoughts about how we're in this specific moment here with defense strategy, semiconductors, quantum and AI, that we're going to see maybe hopefully another renaissance that's the creation of technologies that are useful for defense, have a lot of other benefits to society and economy.
Gary, it's a great point, which actually kind of shifts me to think about with the framework of the model. Usually this is the bleeding edge of innovation that requires a lot of money without guarantees that you're going to have a large volume, and that's very typical for development that is being done on that. And speaking about other countries, DARPA was that vehicle developed by US to drive that. And a lot of the innovations that actually got commercial applications outside of defense and aerospace were done with DARPA money. Now, the companies that are in this space usually face different choices because you can decide to stay and serve very small niche market, which is the defense market, and drive low to medium sized volumes with high margins. And a lot of people are comfortable in this space. But if you want to actually get the real benefit of the industrial strategies, this is where you start. But in the end of the day, you actually get the larger commercial market, and you get this 5 to 95% ratio of clientele, but you actually serve both markets. And it's a choice that certain companies and leadership and executives and board of directors have to speaking about how the world is dealing with this. I'll give you an example. In UK Department of Defense, I don't know how it is called in UK, but the equivalent of our D&D, they purchased a commercial fab from large publicly traded company. They hired management to restructure the fab, but they wrote them a check and say, I buy 20% of the fab capacity for the next 10 years on very high rates, and that gives them a baseline to run their business. I would love somebody to do this for CPFC. And seriously, because that's the way how you do it. The other problem that we are facing. Sorry, go ahead.
Same thing. Global Foundries were annoyed at their automotive customers who kept on cutting and swerving. Increasing orders, dropping orders. So they just said you're going to prepay for your fab for the next couple of years. So they got big chunks of money.
Yes. But I think there is another facet of the problems that we are facing in our defense innovation ecosystem. If you can speak that way, we lack system integrators, and that's the critical point in the supply chain that can make it or break it. Because we all have abilities to move the innovation from R&D to NPI. When it comes to module chips devices, even on the quantum, I don't want to oversimplify the thinking. If there are people in the quantum world that are on the call, probably won't be happy with what I'm going to say. But in the end of the day, you have to make a chip. There is quantum technologies are semiconductor technologies. And you can push the envelope on the performance of the chip, on the material system, on the accuracy of your and the tolerances and all that. But at the end of the day, you have to make a chip. The question is what you do with it. Who's gonna take it, integrate it, and put it in a real? Companies are coming to us for rangefinders. Between what we do and a full rangefinder, there are five layers in the supply chain. So how we bridge that?
Well, we alluded in the title of this webinar that this is a Mars shot, and as someone who's a really big fan of the space program, I think the moon shot was sort of the impetus to take all those technologies and integrate them so we could put people in space and bring them back. And we're starting to put people in space again. So that might be globally maybe some inspiration. But it seems to me that we have all these technologies. How can we coalesce them the right way to solve problems? Big problems that we need a lot of volume for. And then, as you say, is sort of with the understanding that there needs to be some investment, some serious investment with understanding that there's a lot of uncertainty in this area. I think that needs to be a shift. Gordon, do you have thoughts on that?
Duet is more a proposal that follows along the lines of fabric, and it has a bit more of a tilt towards things that could be dual use. But in fact, when I used the term Mars shot, I was really looking for some great big initiatives that we could do here in Canada that would really put us on the map. So imagine there's the Snow Lab, the Sudbury Neutrino Observatory, which is 2 kilometers underground. It's a 1 meter sphere. They want to do a 3 meter sphere, and it's entirely lined with single photon avalanche detectors with a custom chip behind them that captures the data and then ships it out via optical fiber. Well, when they built that 3 meter sphere, they made millions of these SPADs, and those SPADs can be used to detect radiation, to detect all sorts of particles. And so imagine you see a cloud and kilometers away. You can put a laser into it and see what particles come out, and you can determine whether it's water vapor or smoke or radioactive dust or whatever. And so that would be to do a whole project around these SPADs, and the SPADs are built where? Teledyne and Bromont, packaged at IBM and Bromont. Yes, multinationals, but still on our turf. And that could be a big thing for us to do. Another thing is we have some companies that build equipment and actually provide a service of delaminating chips, taking them apart and having a look underneath them. So that too could be a really useful service for us to develop as probably a defense priority. They would want to know if they capture someone else's equipment. They want to see how they did it and what technologies they used and so on. So that could be a very defense-related kind of activity. But at the same time, it could do commercial stuff for folks who understand the failure of their chip and maybe many million layers of oxide and metal down before you can see where the failure is. And so I've got 5 or 6 of those sorts of ideas that are what I call the Mars shots. Another thing is imagine Area.xo and Invest Ottawa have this proving ground for e-mobility. Well, imagine if we did a test and integration center for drones, and we tried to spoof the cameras and spoof the AI and find out ways of causing them to fall. That could be an outsourced test and integration center OTIC for drones. So there are lots of things we could do as a big bricks and mortar kind of facility that would have some.
It's sort of making us the go-to country for specific things, and that leads us back to the CPFC. And since we're almost out of time, Velko, you have any final thoughts on being one of the go-to facilities, hopefully not just in Canada, not just in Canada, but already like building that up. That we have that cachet, credibility in the global stage.
Well, I think going forward, there will probably at least three core challenges to first of all to be able to support the ecosystem and help the companies to scale up. Because if you look at the journey of the clients that we work with, a lot of the Canadian clients we have are at the scale up stage. So the question is not whether we can make it. The question is whether we can make it in volumes. And if people think volumes are small they're not. We're talking about hundreds of millions of devices of a particular class. So scaling up to support the scale up of the ecosystem is very important. And that actually brings two challenges: maximizing the capacity of the current fab, and perhaps pave the way to build a larger fab. So we can actually go and offer way larger capacity and keep those clients happy over the time. The other thing is if you look at the supply chain from raw materials to substrates to wafer fab to backends to packaging, we have a lot of gaps. So we have to expand the scope of services. And part of our defense industrial strategy funding that we got through the umbrella of the National Research Council of Canada is actually to develop and functionalize a pilot facility that can do non-good die from all the process wafers that and then we can partner with the ecosystem in Brumont and some of the ecosystem in Canada to actually package those devices. So building this integrated type of supply chain is the other big challenges. The other thing is we made a conscious selection of what type of materials we're going to work with. And over time, we probably will look at other materials, but we have to look at the partnership. And somebody was posting about thin film lithium niobate, which is a material of choice for modulators. We have parts of the ecosystem here that understand that material system. Would love to work with them. Integration with silicon and silicon nitride it happened to be very challenging because you have competing technologies. You also have different paths of doing that. So for us, this is also very important to work with the right partners domestically, internationally to do that.
Well, we're over time, and I really thank folks for joining us. And I think that's a good place to leave it because it gives people some homework to see how they can get involved and contribute to addressing these things.
Thank you all for hanging on. A really interesting talk from my point of view. I hope you enjoyed it. I enjoyed the chat.
Thank you so much.
Bye.
Good afternoon.